Hello. In this video, I'm going to look at the t-distribution and confidence interval. So we've looked at the normal distribution table, which in any case deals with a random variable that's been standardized to be z. But we also have what is known as the t-distribution, or the student's distribution, where basically the intention was that it would be for primarily small samples. So with the t-distribution, you have that essentially the standard deviation is unknown. So in that case, that means that it would have to be based on some random sample, with the sample size being n. Now, notice that here on the chart, we have a standard t-distribution, and it has the area that lies to the right of the tail. Now, of course, the thing about this is that there's a column that represents the degrees of freedom. And the degrees of freedom actually, if you think about it, it's that if we have, let's say, for example, 5 pieces of candy, like chocolate perhaps, and you're to distribute those amongst 5, well, you have that the first 4 could pick anything in either case. But the last one has no choice, actually, because once all of the selections have been made, then it's kind of forced in that sense. And the same thing goes for the sample standard deviation, where you saw that there was the degrees of freedom in which that mostly had to account for rounding error and also these biases in any case. So we have that degrees of freedom would be introduced for things of which that the standard deviation is not known, and we take a random sample. Now, one thing that we can say is that for the distribution, like if we were to try to standardize this, then in any case, that would be where you would take that t is equal to x bar minus the mean divided by the standard error, which in this case, the standard error is our sample standard deviation, divided by the square root of n. So this gives it kind of like a perspective as to, how do we determine a t value, for example. But in any case, this still follows what we say to be our t distribution with the n-1 degrees of freedom. So what we could do, for example, is say, what if we had a sample size and we had that n-1 was equal to 21? So that means that this, in fact, is our degrees of freedom. So this is our degrees of freedom. But let's say that this alpha, in this case, is 0.0, let's say 0.05. Okay, so we have that t is going to be 0.05, and just for reference, we'll just put that that's going to be with 21 degrees of freedom. So in this case, what we could do is just look at the 0.05. So we have this, and then we look for 21, which that would be this column or row. So we look for that, and we get 1.721. So this means that the critical value with respect to our t distribution, such that the area to the right is 0.05, that's going to be 1.721. So here, we could use this perhaps like for any given t distribution and also a confidence interval. Now, if, for example, that we wanted to know perhaps another type of t distribution such that the alpha would be 0.01, and then in this case, if we were going to write the degrees of freedom to be 14, well, it's the exact same thing where you basically just look for the alpha region, which in this case is the 0.01, and then we look for the row with 14 degrees of freedom, and that would be 624. So we have that this would be our critical value with respect to using alpha to be 0.01 and then the degrees of freedom to be 14. Now, as you see, like in the confidence interval that we have above here, this confidence interval actually has, the alpha over 2. So think of it this way. So if we know that basically we have a confidence level, then in that case, we just have to assume that it's two-tailed, which we have the area to the right, is our alpha over 2 in actuality. So see like how in this case this is 0.05, but that's already accounting for that's half of the alpha region, which would be 0.1. So this would correspond essentially to a 90% confidence with 21 degrees of freedom. But then this one over here, if this one accounts for the same thing for the alpha over 2, then basically that means that this would be the 98% confidence level with 14 degrees of freedom. And of course, like if you would think of it in terms of, visually, you could say, well, let's take 1 minus the confidence level. So in that case, we have 0.90, and this would equal to our alpha in either case, which would be equal to 0.1. But then dividing that by 2, that's where you get the 0.05. And then similarly, 1 minus 0.98, the confidence level, that will equal to, similarly, it equals to alpha in either case. But remember that when you get it, the alpha region, you have to divide by 2. So you have 0.01, or I guess we can say 0.02 divided by 2, and that will be 0.01. Now, if in fact like you wanted to use the calculator, well, instead of using these table values, basically what we could do is just use the calculator to determine these. Now, pictured here, you see that we could find the area to the left of our t-score, which the alpha region would have to be, the alpha, or our area of region would be the alpha over 2. So this is 0.05. But see like how it says 0.9499? That's the 95% that would account for the left side of this. And then you see that the degrees of freedom is 21. And of course, what is the t-score? The t-score in this case says that it's 1.72. Now keep in mind that if you are using a student's t distribution table, distribution, well, it's not the same as the standard normal curve, but it's very similar as the sample size gets bigger in either case. So let's say that, for instance, that we didn't have perhaps like a chart, but we did have a calculator, and we can see like what we would do to find that. And that would be going to second vars, use the inverse t function, and from there we would have to basically tell the calculator the area, which in this case would be 0.95, and then we would have to tell it to use the degrees of freedom as 21. Let's see if this works. Okay, So it's allowing us, or it's telling us that the t-score for this one would be 1.72. Now, normally there is a menu that would pop up for this calculator, but let's see if it does. Yeah. So here, see like how we could do the same thing for the area. And if we look back at the area for this one was 0.01, which means that the area in this case would have to be 99%. So because you're accounting for basically the extra amount on the end of it, because we assume two-tailed. So 0.99, and then for this one we used 14 degrees of freedom. Now keep in mind that that means that the sample size for this one would be 15. So that means that you have 14 degrees of freedom, whereas the 15th sample, it has no choice, essentially. So we just do this, and we get 2.62. Now see like how the numbers are kind of off in terms of like, well, on our chart it said something else, right? It said 1.721 and some change, and then 2.62 and some change. That's fine. So if we're going to use the table, or if we use the calculator, essentially, I mean, you're still getting the same result, really. Now, I won't go through like how we can find a probability, but in either case, like, that is something that can be looked at. If we had a t-distribution and we had that we were dealing with a small sample size, then yeah, we could probably find the probability of a specific event given the standard deviation, the sample size, and then also the sample mean. Now, what we can do is say, well, let's suppose that we wanted to construct a confidence interval where we determine information or a point estimate about how many hours a week an online student will work. So suppose we'd like to know how many hours per week online students at LSCS work. If we take a sample of 20 students and find a mean of 16.3 hours with a standard deviation of 5.4 hours, construct a 95% confidence interval for the average of all, see that it says all, LSCS students. Now keep in mind that this sample size, by definition, is actually pretty small. So we can probably, say that, well, if we don't know what the population standard deviation is, and also what the mean happens to be, then it's by definition meaning that we can still use, or we could use, a standard t-distribution for this. So for this one, if we're looking at a 95% confidence, then in that case we know that it's 1 minus 0.95, of which in this case, if we go ahead and we look at this, that's going to be 0.05. So this is our alpha. Now, in that case, though, that would imply that the t-value that we need to look for is actually half of that. So that's 0.025. But how many degrees of freedom would that be? If it's a sample of 20 students, then that's going to be 19 degrees of freedom. And for this one, we would basically just use also that we can determine that the sample mean is given because it says that they find a mean of 16.3 hours. Okay, so we have 16.3 hours. And then essentially they took a sample, right, to determine the standard deviation, and that was given to be 5.4. So we have 5.4 hours. Okay, so that's S, right, the standard deviation. And what is N? N is 20. So we have that the only thing that we actually need is the t-score. And what we can do here is then look at, well, we know that basically part of the area accounts for, what's to the left of it. So if we take 1 minus 0.025, then we're looking at 97.5 to be the area. So we'll do this. We'll do second vars inverse t, and we're going to replace the area with 0.975. The degrees of freedom is 19 due to the fact that we have a sample size of 20. So n minus 1, 20. And then we hit enter. And the approximation for this is 2.093. So we have that this is equal to 2.093. But remember that we were constructing a confidence interval to estimate basically on average how many hours that a student would work. That's an online student. So 16.3 plus or minus. Okay, so we take 2.093, we multiply by 5.4, but this is divided by the sample size of 20. Now keep in mind that this part right here represents the margin of error. Okay. So here we'll maybe we'll take the computation of using 2.093 multiply by our standard deviation of 5.4, and we'll divide that by the square root of the sample size, which is 20. So what I'm calculating right now is actually the margin of error. So we find that the margin of error is 2.5. So that's 2.5 hours. So we'll go ahead and write this to be 16.3 plus or minus. Okay, so that would be, we said 2.5. And when we go ahead and we compute this, we'll go ahead and find that when you take 16.3 minus 2.5, that's going to give you 13.8. Okay. And similarly, if we take 16.3 and we add the 2.5, you get 18.8. Okay, so yes. Okay, so that would be 18.8. And, one of the things of which that we have here is that somewhere on this interval line that we have the average of all Lone Star College students online, or online Lone Star College students, and how many hours that they work. So this is our 95% confidence in this case for the number of hours worked per week to be 13.8 and 18.8. Now keep in mind that if we were going to find the point estimate given the confidence interval, then you would just be adding actually the two endpoints and dividing by 2. And then similarly, if we wanted to find, if we were given the confidence interval and we were given perhaps like the sample mean, we can get the margin of error as well. Now, if, for example, that we had this statistics already, like the sample mean, the standard deviation, and the sample size, or the degrees of freedom, that is, because remember that degree of freedom, it's given by n minus 1, which in this case was 20 minus 1, which is 19. So degrees of freedom is 19. So let's say that we wanted to find the same thing, but a lot faster. So, I think it's stat. Yeah. So go to stat, go to tests, go to the t interval, and here we're just inputting the statistics that we already determined, for example. And that statistic was that on average, based on the sample, that students that are online, that they work about 16.3 hours online. The standard deviation was already determined to be 5.4 hours. Now, notice that here, you just have to input the sample size, not really the degree of freedom. Okay, but it's good to know the degrees of freedom, that is. And we were using a 95% confidence, which if we alter it, to 90%, then we know that the confidence interval is going to get smaller. But we could also look at, what happens as you make the sample size bigger in any case. Okay, so see how we have that the endpoint is 13.77, which of course rounded would be 13.8. And then over here we have that this gives us 18.8. So now we see that we can actually get a confidence interval if we already have the statistic for the sample mean and the statistic for the standard deviation. Now, if possible, think of what if we didn't have actually these statistics, but we had the data? Then what would you do? The answer to that would be that you would essentially just calculate the sample mean and the standard deviation respectively. But note that this calculator would actually allow you to input that data and then conduct the t-interval, of which that you're just telling it specifically what the data was, and then from there the calculator will find basically the sample mean, the standard deviation, and knowing the sample size, given that you're inputting the data, that is, then it will then determine that confidence interval. And yeah, you have to indicate the confidence level, that is. So typically, like, it could be like 99%, 95%, 90%, and so on. And in either case, just remember that the t distribution is only when we don't have any information about the population mean and the population standard deviation, because that's kind of the whole point, is that we're trying to estimate these parameters, and specifically which one. It would actually be the mean, actually the mean average, that is.